Now we take up a very useful result. If a function fx is such that limit x approaches a, fx is 0. Its limit as x approaches a, fx is 0. And second is, there is another function gx which satisfies the condition that m is less than equal to gx is less than equal to m in a deleted neighborhood of a. Deleted neighborhood of a will mean a neighborhood of a except the point a, in which the point a has been deleted. So if a function fx is such that limit x approaches a, fx is 0, and there is another function whose values lie between two real numbers m and m, or this can also be written as if gx is less than equal to k in a deleted neighborhood of a. This form can always be changed into mod gx is less than equal to k. So you can understand the result in terms of these two numbers or mod of gx is less than equal to k. That is, if the values lie between m and capital M, or its modulus is less than equal to k in a deleted neighborhood of a, then limit x approaches a, fx into gx must be equal to 0. Now if this limit tends to 0, and we do not know the limit of gx, but we know only the fact that gx is bounded, that is, its values lie between two real numbers. If fx tends to 0 and gx is bounded, then this limit will be 0. This is bounded, this is finite, and this is tending to 0. So 0 into finite will be 0. So if this limit tends to 0 and this is bounded, then this limit must tend to 0. Now we take up some questions based on this. Now we are given the function fx is equal to x square sine 1 by x if x is not equal to 0, and this is 0 if x is 0. If x is 0. And we have to discuss the continuity of the function this at the point x equal to 0. So what we have to find is limit x approaches 0 of fx and check whether this is equal to f of 0 or not. This is equal to f of 0 or not. If it is equal to f of 0, the function will be continuous, and if this is not equal to f of 0, the function will be discontinuous. So we have to find limit x approaches 0 of fx. Now what we notice, this function x square limit x approaches 0, this will tend to 0, but as x approaches 0, this will be infinity. 1 over 0 will be infinity. So sine of infinity is not known, so value of this limit is not known, but we know that mod of sine x is always less than equal to 1. That is, the values of sine function always lie between -1 and 1. So this is known, that this is bounded. So we apply the result we have discussed just now. You can see the side sheet. So what we do is we consider two functions. Say gx is equal to x square and hx is equal to sine 1 by x. Now limit x approaches 0 of gx is equal to limit x approaches 0 of x square, and this is equal to 0, and mod of hx is equal to mod of sine 1 by x, and we know mod of sine theta is always less than equal to 1. We know mod of sine theta is always less than equal to 1. That is, the values of sine theta always lie between -1 and plus 1. So this is bounded. Therefore, we apply the result we have already discussed, and limit of x approaches 0 of gx into hx will be equal to 0. That is, limit x approaches 0 of gx, that is x square, and hx is sine 1 by x, will be equal to 0. So we have applied this result and found that this limit will be 0. On similar lines, you can try these questions. This is product of two functions. This is gx and this is hx. Now, as x approaches a, this will tend to 0. And mod of this will always be less than or equal to 1. So this is 0 and this is bounded. So limit will be 0. In this case also, as x approaches 0, mod of x will tend to 0. And sine of 1 by x is bounded. Mod of sine theta is always less than or equal to 1. So this is 0 and this is bounded. And therefore the limit will be 0. You can try these questions on similar lines. Now we discuss continuity of a function in an interval. Now first we discuss the continuity of the function in the open interval AB. A function fx is said to be continuous in an open interval AB if it is continuous at each and every point of a, B. A function is continuous in an open interval AB if it is continuous at each and every point of AB. Next is continuity in closed interval AB. A function fx is said to be continuous in the closed interval AB if and only if first is fx is continuous in the open interval AB. It is continuous in the open interval AB. This is the closed interval AB. This closed interval is the union of the open interval AB and the point A and point B. This is open interval AB plus this point and this point. It is the union of open interval AB and the point A and the point B. So first of all, we must check that this is continuous in this open interval AB. And second thing is, it should be continuous at this point, but these points are not in this interval. So we cannot approach A from this side. We cannot approach A from this side. We can only approach A from points within this interval. That is from this side. So that is from the right side. We must check the continuity of this function from right. That is, fx is continuous from right at x equal to a. That is, limit x approaches a from positive side, fx must be equal to f of a. We can only check the right continuity. And third is, fx is continuous from left at x equal to b. That is, limit x approaches b from left, because these points are not inside this interval. So we cannot approach b from right. That is, points greater than b. We can only approach b from left. So we can only find the left-handed limit at fx. So this must be equal to f of b. So this function will be continuous in this closed interval AB if and only if it is continuous in closed interval AB. It is continuous from right at x equal to A and it is continuous from left at x equal to b. So these three conditions must be satisfied. That is, it is continuous in the open interval AB, continuous from right at A and continuous from left at B. Then it will be continuous in closed interval AB. And note, a function which is continuous in closed interval AB must be bounded in this interval. A function which is continuous in closed interval AB must be bounded in this interval. But this result is not true for open interval AB. For example, fx is equal to 1 by x in 0, 1. Now this function is continuous in this interval, but it is not bounded, because as x tends to 0, fx tends to infinity. So at points very close to 0, this function will tend to infinity. Therefore, it is not bounded. It is continuous but not bounded. Only point of discontinuity of this function is x equal to 0, but 0 is not in this interval. Third is continuous function. A function is said to be a continuous function if it is continuous in its domain. Continuous in its domain of definition. And fourth is continuous everywhere. Everywhere. If it is continuous throughout the real line, continuous in whole of the real line. It is continuous for every real number. It is continuous on the whole of the real line, then we say that it is continuous everywhere. A function is said to be continuous if it is continuous in its domain of definition. And if that domain of definition is equal to R, that is, it is continuous in whole of the real line, then we say that it is continuous everywhere. We will prepare a list of some common functions which are continuous in their domains. First function is the constant function, that is fx is equal to k. This function is defined for all x, so its domain is R. It is defined everywhere, and fx equal to k, therefore at x equal to, say, this point, the value of the function will be k. At this point, again the value of the function will be k. At every point, the value of the function will be k. So this function will have a graph which is a straight line parallel to the x-axis. So this will be the graph of this function, and distance of each point on this graph from x-axis will be k. So for constant function, domain is R and graph is this, and this function is continuous at each and every point of its domain R. Second is identity function. Fx is equal to x. This function is defined for all x. Linear in 2 dimensions represents a straight line. So this is a straight line, and to plot a straight line you need only 2 points. 2 points define a complete straight line. So let x be equal to 0. When x is 0, value of the function is 0. 0, 0 is 1 point. At x equal to 1, value of the function is 1. We join these 2 points and get this straight line. Or we can use coordinate geometry. This line is y is equal to x. So slope of this line is, we can compare it with y is equal to mx plus c. So m is 1 and c is 0. This line is passing through the origin. So when slope is 1, therefore tangent theta is 1 and therefore theta must be equal to 45. So we can plot this line with theta is 45 and this line is passing through the origin. So this will be the graph of this line, and this graph is continuous throughout. So this function is continuous throughout the real line. Such functions are known as everywhere continuous. This function is everywhere continuous. This function is also everywhere continuous. Now we come to fx is equal to mod of x. Fx is equal to mod x. Fx is equal to mod of x. This is equal to x if x is greater than equal to 0, and this is minus x if x is less than 0. Now for both these straight lines, for first one m is 1, therefore tangent theta is 1, and this implies theta is 45 degrees. And for this line, y is equal to minus x, m is minus 1. You can compare it with the y is equal to mx plus c. So m is coefficient of x, that is minus 1. Therefore tangent of theta is minus 1, and this implies theta must be equal to 135 degrees, or you can say 3 pi by 4. This is 3 pi by 4. This is pi by 4. So this angle is 3 pi by 4. So this we can say this is pi by 4. This is pi by 4. Pi minus pi by 4 is 3 pi by 4. So this is the graph of the modulus function. Modulus function has V-shaped graph. This is the V-shaped graph, and this graph is continuous everywhere. So this function is continuous throughout its domain. This function is everywhere continuous. Now next is exponential function. Fx is equal to ax. This function is defined for all r, for all real numbers. A graph of this function is, if a is greater than 1, shape of the graph is this, and if a is less than 1, shape of the graph is this. If a is greater than 1, say a is 5 to the power of x. Now when x is 0, 5 to the power of 0 is 1. So when x is 0, value of the function is 1. So this is the point 0, 1. And when x is 1, x equal to 1, value of the function is 5. X equal to 2, value of the function is 5 square, that is 25. So what we notice, at x equal to 0, value is 1. X equal to 1, value of the function is 25. At x equal to 3, the value of the function will be 125. So there is a steep rise in the values of this function. So there is an exponential growth in the values of these functions. And if x is less than 1, say x is minus 1, x equal to minus 1, then this will be 1 by 5. X equal to minus 2, this will be 1 by 25. So values of the functions will decrease exponentially. And as x tends to minus infinity, value of the function will also tend to 0. So as x tends to minus infinity, value of the function will be very, very small. So it will tend to, value of the function will tend to 0. So as x tends to minus infinity, value of the function will be nearly 0. It will never be 0. So this graph will never touch this line, but will be very close to this line. And as x tends to infinity, graph will rise to infinity. And for a less than 1, let fx be equal to 1 by 5 to the power of x. So when x is equal to 1, value of the function is 1 by 5. When x is equal to 2, value of the function will be 1 by 5 square. That is 1 by 25. At x equal to 0, value of the function will be 1. Anything to the power of 0 is 1. So value will be 1. X equal to 0, value is 1. X equal to 1, 1 by 5. X equal to 2, 1 by 5 square. So what we notice at x equal to 0, value is 1. At x equal to 1, it will be 1 by 5. It will be smaller than this, 1, 5. And at x equal to 2, it will be still smaller, that is 1 by 25. So what we notice, values of the function are exponentially decreasing, or sharply decreasing. And when x is, say, minus 1, the value of the function will be 1 by 5 to the power of minus 1, that is 5. And at x equal to minus 2, value will be 1 by 5 to the power of minus 2, that is 1 by 5 to the power of minus 2, that is 25. So when x decreases, the values of the function increase exponentially. There is a sharp increase in the values of this function. As x tends to infinity, values of this function will tend to 0. So as x tends to infinity, values of the function will tend to 0. And here as x tends to minus infinity, values of the function will increase to infinity. So these two graphs you must keep in mind. For a greater than 1, the graph rises exponentially. And for a less than 1, it falls exponentially. So graph of this function for a less than 1 will be this. And for a greater than 1, it will be this. Now next function is logarithmic function. Fx is equal to log x to the base a. Domain of this function is all those real numbers which are greater than 0. That is 0 to infinity. And graph of this function for a greater than 1 is this. And graph of this function for a less than 1 is this. And from here we can note, as we know, for x equal to 1, log of 1 to the base a is 0. A may be greater than 1, it may be less than 1. So for x equal to 1, y must be 0. So x equal to 1, y is 0. So this is the point. And here also x equal to 1, y must be 0. So this graph touches the x-axis at 1, 0. And here it touches the x-axis at 1, 0. And in this, for a greater than 1, what we notice, as x tends to 0, fx tends to minus infinity. As x tends to 0, x is very close to 0, value of log will be minus infinity. It will be minus infinity. And as x tends to infinity, fx will tend to, as x tends to infinity, this will keep on increasing and this will go to infinity. So this will be infinity. And for a less than 1, what we notice, as x tends to 0, fx tends to infinity. Fx will tend to infinity. And as x tends to infinity, fx tends to, as x tends to infinity, we can note from the graph that it will tend to minus infinity. Value of the function will tend to minus infinity. So these things you can note from the graph. You must keep these two graphs in mind. And when we will study inverse functions, we will note that these two functions are inverse functions, inverse of each other. And so the graph of this will be the mirror image of this graph in the line y is equal to x. Y equal to x. For inverse functions, if we have two inverse functions, f and f inverse, their graphs will be mirror image of each other on the line y is equal to x. So on the line y equal to x, this graph will be mirror image of this. We can obtain the graph of log by taking the mirror image of this graph in the line y is equal to x, and similarly for these. Now we come to the trigonometrical functions. We have already studied the graphs of these functions. I will briefly discuss these graphs and continuity of these functions. Fx is equal to sin x. Domain is whole real line. This is defined for all real numbers. And graph of this function is this. For sin 0 is 0. X equal to pi by 2, sin pi by 2 is 1. For x equal to pi, sin pi is 0. For x equal to 3 pi by 2, value of the sine function is minus 1. So this is the point. At 2 pi it is 0. So this is the graph, and similarly you can plot it on this side. And we can see from the graph that it is a continuous graph. So this function is continuous throughout the real line. This function will be called everywhere continuous. This function will be log of x to the base a is a continuous function. This is also a continuous function, but this function is continuous in its domain, and this is continuous in its domain, which is also the real line. So this is everywhere continuous, and this function is called a continuous function. This is continuous function and continuous everywhere, but this is continuous only in its domain. Cos x is again defined for all real numbers, and graph is this. X equal to 0, cos 0 is 1. Cos of pi by 2 is 0. Cos of pi is minus 1. And cos of 3 pi by 2 is 0. Cos is 0 at odd multiples of pi by 2. And sine is 0 at multiples of pi. Sine is 0 at multiples of pi, and cos is 0 at odd multiples of pi by 2. Next is fx is equal to tangent x. Fx is equal to tangent x, and domain of this function is all those are except the points where cos x is 0. Tangent x is sin x over cos x. So denominator should not be equal to 0. So we will have to leave those points where cos x is 0. And I have told you that cos x is 0 at odd multiples of pi by 2. That is, we have to leave the points which are odd multiples of pi by 2. N is any integer. So domain is R minus odd multiples of pi by 2. And graph is this. And we can note that this function is not defined at pi by 2. So this graph will not touch this line. It will be very close to this line, but will not touch this line. It will be minus infinity and then go to infinity. Minus infinity and go to infinity, but they will never touch these lines at odd multiples of pi by 2. This will never touch pi by 2. This will never touch 3 pi by 2. And fx is equal to cotangent x. This is cos x over sin x. So denominator should not be equal to 0. So domain will be r minus x such that sin x is 0. We will have to leave the points where sin x is 0. And we know sin x is 0 at multiples of pi. So r minus multiples of pi, that is n pi. And graph of cotangent is this. And here what we notice, this graph will not touch the line x equal to 0 because cotangent x is not defined at x equal to 0. So this graph will never touch this line. N equal to pi, this function is not defined at pi. So this graph will not touch the line x equal to pi. It will be very close to this line but will never touch this line. And next is fx is equal to secant x. This is 1 over cos x. Denominator should not be equal to 0. So r minus x such that cos x is 0. This will be the domain. R minus cos is 0 at odd multiples. So we will have this as the domain, same as this. And graph is this. And this graph will not touch the line pi by 2, 3 pi by 2, because secant x is not defined for these points. So this graph will be regarded as a continuous graph because it is continuous at all points of its domain. This is not continuous at pi by 2, but pi by 2 does not belong to the domain of the graph. So this will be called a continuous function because the points at which it is discontinuous, they do not belong to the domain of the function. The graph is breaking at these points, but these points do not belong to the domain. And next is fx is equal to cosecant of x. Cosecant of x is 1 by sin x. Sin x must not be equal to 0. So you will have to leave those points where sin x is 0. That is n pi, same as this. So graph is, and we note that this graph will not touch the line 0 and pi, minus 2 pi, and so on, multiples of pi, because they do not belong to the domain of this function. This function will be regarded as a continuous function because these points where it is breaking, the graph is breaking, they do not belong to the domain of this function. Next is a polynomial function. Polynomial function. Fx is equal to an xn minus 1 plus an minus 1 xn minus 1 plus so on plus a1x plus a0. Polynomial function is a function of this type in powers of x. And this function is defined for all real numbers. For all real numbers. And the graph of this function will vary from polynomial to polynomial. But it will always be a continuous graph. Graph of any polynomial function may differ from polynomial to polynomial, but all these graphs will be continuous graphs. So domain of continuity of a polynomial function will be R. Rational function. Rational function is a function of the type polynomial over polynomial. Polynomial over polynomial. A polynomial px over polynomial qx. And domain of this will again be denominator should not be equal to 0. So all those real numbers except the points where qx is 0. Leave the points where qx is 0. And graph of these rational functions also vary from function to function. But all these graphs will be continuous in their domain. That is at the points where qx is not equal to 0. Because the points at where qx is 0, they do not belong to the domain of these functions. So these functions are continuous everywhere, continuous everywhere, continuous everywhere, continuous everywhere. This is a continuous function. This will not be called a continuous everywhere function. It is continuous in its domain. We will say logarithmic function is a continuous function, but it is not continuous everywhere. It is continuous in its domain only. This is continuous everywhere, continuous everywhere. This is a continuous function because it is continuous in its domain. It is not continuous everywhere. Continuous in domain, not continuous everywhere. Continuous in its domain, not continuous everywhere. This is continuous but not continuous everywhere. This is continuous everywhere. This is continuous function. This is not continuous everywhere. Note, not all the functions are continuous in their domains. For example, fx is equal to integral value of x. Now domain of this function is whole real line. This function is defined for all real numbers. But this function is not continuous for all real numbers. It is not continuous for integral points. At integral points, this function is not continuous. So this function is not continuous function. Algebra of continuous functions. Let fx and gx be two functions which are continuous at x equal to a. A is any real number and c be any real number. Then first is c of f is continuous at x equal to a. Then c of f is continuous at x equal to a. Second is f plus minus g is continuous at x equal to a. Third is f into g is continuous at x equal to a. And fourth is f over g is continuous at x equal to a, provided g of a is not equal to 0. This function is not 0 at x equal to a. Then this will be continuous at x equal to a. 1 upon g is continuous at x equal to a, provided, again denominator should not be 0, provided g of a is not equal to 0. G of a is not equal to 0. And this concept can be extended to, let d1 and d2 be the domains of continuity of f and g. Then cf is continuous in domain. Domain of f is d1. So this will be continuous in d1. And second is f plus minus g is continuous in d1 intersection d2. That is, it will be continuous in the domain common to both these functions. Intersection of these two domains. That is, it will be continuous in the domain which is common to both these functions. And third is f into g is continuous in, again, d1 intersection d2. That is portion common to both these domains. And fourth is f over g is continuous in d1 intersection d2, provided g of x is not equal to 0. That is, we will have to leave the points where gx is 0. And fifth is 1 upon G is continuous in D2. Domain of G is D2, provided G of X is not equal to 0. So this concept can be extended to the domains of continuity in this manner. Now we take up some questions depending upon these, and I have already told you the domains of some continuous functions. In this question, we have to discuss the continuity of cosine function. Let fx be equal to cos of x. The domain of this function is cos x is defined for all real numbers. So domain of this function is R. Let A be any point of R. Now to check the continuity of the function in R, we take a point in R and check the continuity of this function at this point. That is, fx is continuous at x equal to a if and only if limit x approaches a, fx is equal to f of a. If and only if limit x approaches a, fx is equal to f of a. That is, if and only if limit x approaches a of cos x is equal to cos a. Now, limit x approaches a of cos x is equal to, put x minus a is equal to t. As x will approach a, t will approach 0. So this limit can be written as limit t approaches 0 cos of x. X is a plus t. A plus t. And this is equal to limit t approaches 0 cos a plus t. Cos a plus b is cos a cos b minus sin a sin b. Use this formula and we get cos a cos t minus sin a sin t. And this is equal to, now cos a is constant, therefore it can be taken out. Cos a limit t approaches 0 cos of t minus sin a is constant, we take it outside and we get limit t approaches 0 sin of t. Now we will use two standard results. Limit t approaches 0 cos of t, this is equal to 1, and limit t approaches 0 sin of t is 0. We will use these two standard results, and therefore this is equal to cos a into limit t approaches 0, cos t is 1. This into 1 minus sin a, and this limit is 0 into 0. This is equal to cos of a. Therefore, cos x is continuous at x equal to a. We took a general point x equal to a and we have proved that cos x is continuous at this general point. Therefore, cos x is continuous everywhere in R. So this is the result. And next is prove that the function fx equal to tangent x is continuous function. So let fx be equal to tangent of x. Then domain of this function is, this is sin x over cos x. So cos x should not be equal to 0. So domain is r minus Now cos x is 0 at odd multiples of pi by 2. So domain will be 2n plus 1 pi by 2. So domain of f is r minus odd multiples of pi by 2. To prove tangent x is continuous function, we shall prove that tangent x is equal to sin x over cos x is continuous in its domain. Now we know sin x, cos x are continuous everywhere. These functions are continuous everywhere, and therefore sin x and cos x are continuous in domain of f. These are continuous everywhere, and therefore these are continuous in domain of f also. Also, cos x is not equal to 0 in domain of f, and therefore sin x over cos x is continuous in domain of f. Now we know if f is continuous in a given domain and g is continuous in that domain and cos of x is not equal to 0, and f over g is continuous in this domain. You can see the side sheet. And therefore tangent of x is continuous in domain of f. Hence proved. Hence proved. Prove that the greatest integer function, integral value of x, is continuous at all points except at integral points. Let a be any real number. Now to prove that the greatest integer function is continuous at all points except at integer points. So we will take a general point on the real line and discuss the continuity at this point. That is, we have to check that whether limit x approaches a of fx is equal to f of a or not. We have to check limit x approaches a, fx is equal to fa or not, if a is any real point. Now we can divide this question into two cases. Case 1 is a is an integer. If a is an integer, then what we do is, let this be the point a. Then the previous integer will be a minus 1 and the next integer will be a plus 1. Now at integral points, I have told you earlier that we must find the left and right limits separately. You can see the side sheet. So what we do is limit x approaches a from positive side, fx is equal to limit x approaches a from positive side, integral value of x. Now as x approaches a from positive side, this will mean that x approaches a from positive side. This will mean x is greater than a in neighborhood of a. That is, at points we are considering the points which are very close to a. So in neighborhood of a, what we see is that x will lie somewhere here. So at these points x is greater than a. So for these points, the integral value of x, that is the integer immediately smaller than this, will be a. I have told you that integral value of x can be interpreted as the integer which is immediately smaller than this number will be the integral value. So if x lies here, then the integer immediately smaller than this will be a. So this will be equal to a. So integral value of x will be equal to a. So this limit will be a. And limit x approaches a from negative side, fx is equal to limit x approaches a from negative side, integral value of x. Now as x approaches a from negative side, x is less than a in the neighborhood of a. We are considering points in the neighborhood of a. So x is less than, so x will be somewhere here. So for x less than a, for points which are less than a in the neighborhood of a, the value of the integral value of x will be the integer immediately smaller than this. Now in this interval, the integer immediately smaller than x will be a minus 1. So integral value of x will be a minus 1. So this will be equal to a minus 1. So right limit is this and left limit is this. Therefore, limit x approaches a from positive side fx is not equal to limit x approaches a from negative side fx, and therefore given function is not continuous at x equal to a. That is, the given function is not continuous at integral points. Therefore, it is not continuous at integral points. Now we consider case 2. A is not an integer. If a is not an integer, then any non-integral point will always lie between two integers, say k minus 1 and k. So a will always lie between two integers. It will always lie between two integers. Therefore, there exists an integer k such that k minus 1 is less than a is less than k. Now, limit x approaches a from positive side, fx is equal to limit x approaches a from positive side, integral value of x. And this is equal to, now x approaches a from positive side, this will mean x approaches a from positive side, x is greater than a in neighborhood of a. That is points very near to a. So at points greater than a and very near to a, the integral value of x will be k minus, immediately smaller than x. Integer immediately smaller than x will be k minus 1. So integral value of x will be equal to k minus 1. So this limit will be k minus 1. Now we come to the left-handed limit. Therefore, limit x approaches a from negative side, fx is equal to limit x approaches a from negative side, integral value of x. And this is equal to, as x approaches a from negative side, x is less than a in a neighborhood of the point a. That is very close to a. Now at points very close to a, say x is somewhere here. So for these points, the integer immediately smaller than this will be k minus 1. So integral value of x will be equal to k minus 1. We can interpret greatest integer function as the integer immediately smaller than x will be the greatest integer function. This is a simplified method of finding the greatest integer function. So this will be equal to k minus 1. So this will be k minus 1. Then what we notice, limit x approaches a from positive side, fx is equal to limit x approaches a from negative side, fx. Both are equal to k minus 1. Also, f of a is equal to integral value of a, and this is also equal to the integer immediately smaller than this will be k minus 1. This is non-integral. So immediately smaller than this will be k minus 1. Integer immediately smaller than this will be k minus 1. Therefore, limit x approaches a, fx is equal to k minus 1, and this is equal to the value of the function at the point a. Therefore, fx is continuous at x equal to a. Therefore, fx is continuous at non-integral points. Hence, proved. Therefore, we have proved that fx is continuous at non-integral points and it is discontinuous at integral points. Now, next question is discuss the continuity of this function. That is, fx is equal to sine x over x if x is less than 0, and this is x plus 2 if x is greater than equal to 0. What we notice, at x equal to 0, this function has two different definitions. For x less than 0, definition is this, and for x greater than 0, definition is this. Therefore, for x equal to 0, we will have to find left and right limits separately. At all other points, we can directly find the limits. Now, fx is equal to sine x over x for x less than 0. And we know sine x is continuous everywhere. And therefore, sine x is continuous for x less than 0. X being a polynomial is continuous everywhere. And therefore, x is continuous for x less than 0. And also x is not equal to 0 in x less than 0. Therefore, since f is continuous for this, g is continuous for this, and g is not equal to 0 in this interval. Therefore, f over g, that is sine x over x, is continuous in x less than 0. Therefore, sine x over x is continuous in x less than 0. Again, fx is equal to x plus 2 in x greater than 0. The point 0 we will take separately, because at 0 the definition of the function is changing. So, for fx is equal to x plus 2 in x greater than 0, x plus 2 being a polynomial is continuous everywhere. And therefore, fx is equal to x plus 2 is continuous in x greater than 0. Because it is continuous everywhere, therefore it is continuous in x greater than 0. So what we have checked is this function is continuous for x less than 0. This function is continuous for x greater than 0. Only point remaining is x equal to 0. Now at x equal to 0, limit x approaches 0 from negative side, fx is equal to limit x approaches 0 from negative side, and as x approaches 0 from negative side, x is less than 0. So this definition will be used. We will have sine x over x, and this is equal to 1. And limit x approaches 0 from positive side of x is equal to, as x approaches 0 from positive side, x is greater than 0. And therefore, this definition will be used. We will have limit x approaches 0 from positive side x plus 2, and this is equal to, as x approaches 0, this will be 2. Therefore, limit x approaches 0 from negative side fx is not equal to limit x approaches 0 from positive side fx, and therefore fx is not continuous at x equal to 0. Therefore, x equal to 0 is only point of discontinuity. That is, the function is continuous everywhere except x equal to 0. So this function is discontinuous. Now next is determine the value of the constant m so that fx equal to this is continuous. Fx is equal to m into x square minus 2x for x less than 0. Now m into x square minus 2x being a polynomial is continuous everywhere, and therefore this is continuous, and therefore this function is continuous in x greater than 0. Also, fx is equal to cos x for x greater than 0. For x less than 0, definition of function is this. For x greater than 0, definition is this. Therefore, at x equal to 0, we must consider the left and right limits separately. So I am not considering this point here. We will have to consider the left and right limits separately for this point. So I am taking fx equal to cos x for x greater than 0. And we know cos x is continuous everywhere, and therefore cos x is continuous in x greater than 0. So what we notice, this function is continuous at all other points except x equal to 0. So therefore we will have to check the continuity of this function at x equal to 0. Since it is given that this function is continuous, so we must satisfy the condition of continuity at x equal to 0. Only point remaining is x equal to 0. Now limit x approaches 0 from positive side fx is equal to, now as x approaches 0 from positive side, x is greater than 0, and therefore this definition will be used. Limit x approaches 0 from positive side cos x, and this is equal to limit x approaches 0 of cos x is cos 0 is 1, and limit x approaches 0 from negative side fx must be equal to limit x approaches 0 from negative side, x approaches 0 from negative side implies x is less than 0. This is less than 0, therefore this definition will be used, and we will have m into x square minus 2x, and this is equal to, as x approaches 0, this is 0, this is 0, so this will be 0, and therefore limit x approaches 0 from positive side fx is not equal to limit x approaches 0 from negative side fx for any m. Therefore no value of m can make fx continuous. Can make fx continuous. Therefore, no value of m exists. Now we discuss continuity of composite functions. We know that g of f at a is defined as g of f a. If fx is continuous at the point a and gx is continuous at f of a, then g of f is continuous at x equal to a. So you can see the definition. What we notice, if f is continuous at a, if f is continuous at a and g is continuous at f a, then g of f will be continuous at the point x equal to a. I am repeating it once again for you. If f is continuous at a, f is continuous at a and g is continuous at fa. F is continuous at a and g is continuous at fa, then g of f will be continuous at x equal to a. Now g of f is continuous at x equal to a. This implies limit x approaches a, g of f at x is equal to value of the function g of f at the point a. Value of the limit must be equal to the value of the function at the point under consideration, that is x equal to a. So this will imply limit x approaches a, g of fx will be equal to g of f a, and this is equal to g of, now since fx is continuous, therefore limit x approaches a of fx must be equal to f of a. Since fx is continuous at x equal to a, therefore limit x approaches a of fx must be equal to f of a. So f of a must be equal to limit x approaches a of fx. So we can understand this result as, if f and g are continuous functions, then this limit can be taken inside. That is, limit x approaches a, g of fx will be equal to g of limit x approaches a fx. This limit can be taken inside. This result can be understood in this way. This is very useful in doing problems. So with this I take up a few examples. For example, discuss the continuity of the function this at a general point x equal to a. Now we know that fx is the composite of two functions. We read this as cos of x square plus 1. This implies it is a composite of cos of x square plus 1, cos and x square plus 1. So this is a composite of, say, hx is equal to cos of x and gx is equal to x square plus 1, and then fx is equal to h of gx. This is equal to h of gx is equal to h of gx. How much is gx? Gx is x square plus 1. and h of x is cos x. So replace x by x square plus 1. So what we get is cos of x square plus 1. So what we notice, this function is composite of hx equal to cos x and gx equal to x square plus 1. And we read this function as this, cos of x square plus 1. H of g, h of g. So h will be this and g will be this. So this function is equal to this. And what we notice, this hx is equal to cos x is continuous everywhere. This function is continuous everywhere. This is also continuous everywhere function. And therefore composite of these two functions will be continuous everywhere, because we have proved that if fx is continuous at x equal to a and gx is continuous at x equal to f of a, then g of f is continuous at x equal to. If these two functions are continuous, then their composite is also continuous. And since these functions are continuous everywhere, that is at all points, this is continuous at all points, this is continuous at all points, therefore at x equal to a also, and therefore their composite will be continuous everywhere. This is 1, this is 2. Therefore 1 and 2 implies h of g x is continuous everywhere. That is at x equal to a. That is x equal to a. At a general point, x equal to a. And this implies cos of x square plus 1 is continuous everywhere. That is x equal to a. I take up one more question based on this result. In this question, we are given fx is equal to mod of sin x plus cos x. Mod of sin x plus cos x. This function is a composite of mod and sin x plus cos x. Read as mod of. So this is a function which is composite of hx is equal to mod x and gx is equal to sin x plus cos x. We can verify that h of gx is equal to h of gx. This is equal to h of gx. Gx is sin x plus cos x. And this is equal to, now hx is this, here x is equal to sin x plus cos x. So we replace x by sin x plus cos x and we get mod of sin x plus cos x. Now h of g x is equal to h of gx, and therefore h of g at pi will be equal to h of g pi. So what we have to verify is if g is continuous at pi and h is continuous at g pi, then this function h of g will be continuous at pi. So what we require is continuity of g at pi and continuity of h at g pi. Now what we see is h of x equal to mod x is continuous everywhere, and therefore h of x is also continuous at, now we require the continuity of h at g pi. So this is also continuous at g pi. G pi is sin pi plus cos pi. So this is equal to minus 1. Since hx is continuous everywhere, therefore hx is also continuous at g pi equal to minus 1. This is continuous at minus 1. Now gx is equal to sine x plus cos x, and sine x is continuous everywhere. We know that sine x is continuous everywhere, and cos x is also continuous everywhere, and therefore their sum sine x plus cos x is continuous everywhere, and therefore gx is continuous everywhere. And since this is continuous everywhere, therefore gx is also continuous at x equal to pi. Therefore gx is also continuous at x equal to pi. We require the continuity of g at pi and continuity of h at g pi. We have already discussed the continuity of h at g pi, and gx is also continuous at x equal to pi, and therefore these two results 1 and 2, therefore 1 and 2 imply h of g x is continuous at x equal to pi. Now h of g x is mod of sine x. H of gx is mod of sine x plus cos x is continuous at x equal to pi. So what we note in this question is fx equal to mod of sine x plus x. That is, it is a composite of hx is equal to mod x and gx equal to sine x plus cos x. H of gx mod of sine x plus cos x. So we can verify that h of gx is this much. And now we have to discuss the continuity of this function at x equal to pi. This is equal to this. So h of g pi will be this. So we have to discuss the continuity of g at pi and continuity of h at g pi. Now hx is equal to mod of, this is continuous everywhere, and therefore this is also continuous at g pi, which is equal to minus 1. And gx is sum of these. This is continuous everywhere, this is continuous, therefore their sum is continuous everywhere, and therefore gx is continuous everywhere, and therefore also at pi, and we get the result. You can see the side sheet for result on composite functions. In this question, we are given the function this, and we have to show that it is continuous for any real number. This function is fx is equal to mod of 1 minus x plus mod x. We read it as mod of this, mod of 1 minus x plus mod x. So this function is composite of mod x and this function. So let hx be equal to mod of x and gx be equal to 1 minus x plus mod x. Now h of gx is equal to, we just verify that h of g is this much. This is h of gx. This is equal to mod of gx. H is mod, so hx is mod x, therefore h of gx is mod of gx, and gx is this much. So this is 1 minus x plus mod x, which is nothing but 1. Now to prove that this function is continuous for all real numbers, let x equal to a be any real number. Let x equal to a be any real number. Now for continuity of composite functions, we have already discussed the result. You can see the side sheet. Now to prove that this function is continuous for all real numbers, we take a general real number and will show that this function is continuous for this real number. So we have to show that h of g is continuous at x equal to a. Now h of g at a is h of ga, and from the result for continuity of composite functions, you can see the side sheet. We know h of g at a will be continuous at a if g is continuous at a and h is continuous at ga. G is continuous at a and h is continuous at ga. Then h of g will be continuous at a. Now g of x is equal to 1 minus x plus mod x. 1 minus x and mod x are continuous everywhere. This being a polynomial, and we know mod x is continuous everywhere. This is polynomial, therefore it is continuous everywhere. Mod x we know is continuous everywhere. And therefore their sum, therefore 1 minus x plus mod x is continuous everywhere. And therefore g of x is continuous everywhere. And therefore g x is continuous at x equal to a. Therefore it is also continuous at x equal to a. Now hx is equal to mod x is also continuous everywhere. This function is continuous everywhere. Therefore h of x is also continuous at x equal to g a. Therefore hx is also continuous at g. So we have proved that g is continuous at a and h is continuous at g. And therefore from 2 and 3 we have fx is equal to h of g x is continuous at x equal to a, and therefore fx is continuous for all real numbers, because this is a general real number.